Hello, I'm going to give a quick video overview of electromagnetic induction. So this goes along with lecture notes 21. There's a lot of different stuff happening in this lecture, and so I wanted to sort of give you a conceptual framework for how to think about it. So the inspiration here is to think about what are the different ways to make an EMF. We use the symbol cursive E to talk about an EMF, and EMF is just another word for a driving voltage. Um, voltage, not voltage. A driving voltage is like whatever is pushing current around a circuit. We already know one way, that's a battery. And that's a type of EMF called an electrostatic EMF. So a battery uses chemical reactions, moves charge around, creates an electric field, and that electric field is responsible for pushing charge through a wire, for example. But there's other ways, and lecture 21 talks about two new ways to generate an EMF. And so those two ways are motional EMF and Faraday EMF. And the interesting and surprising thing about these two types of EMF, so they satisfy the exact same formula. The absolute value of the EMF is the absolute value of the rate of change of magnetic flux over time. That's delta phi b over delta t. And this equation is called the flux rule, since it talks about the flux. So what's happening? Motional EMF comes from moving a circuit, i.e. like a loop of wire, through a magnetic field. When you move charges through a magnetic field, they experience a force, QV cross B, and if the magnetic field conditions are right and the wire, which is full of freely moving charges, is moving, all those charges have some velocity v. That means they have this Lorentz force, this magnetic force QV cross B, and that force can push charges through a circuit. So on the other hand, it turns out that computing this is pretty hard, except in one particular example of a rectangular loop that you solve in lecture 21 notes. The rectangular loop, you can calculate this exactly. But in general, there's a simpler formula. It's called the flux rule. And instead of computing the Lorentz force on all the charges, you instead compute the change in magnetic flux divided by the change in time. The magnetic flux is the magnetic field times the area of the loop of wire times the cosine of the angle between the loop and the field. And all those things are defined by this little picture. The area is shaded here. The angle is the angle between the normal vector of the loop, so perpendicular to the loop, and the magnetic field. So you get the maximum flux when all the field lines go perpendicular through the loop. That's when theta equals 0. The important thing to remember about the flux rule is these deltas. If your magnetic flux isn't changing, you're not inducing any EMF. There will be a magnetic force, but the magnetic force will cancel out around the whole loop if the flux is constant. So you've got to have part of your loop leaving the magnetic field, as an example. That would create an imbalance and result in a net EMF, and at the same time, a change in magnetic flux. And so the flux rule will work. Okay, so that's cool. That is using magnets to power electric circuits. This is how electric generators work. And it's sort of the basis for all of our modern power infrastructure. But there's something more interesting underlying all of this. So we have to use a little bit of relativity. And relativity is just saying that if you look at something from a different frame of reference, it should work the same. So a motional EMF could come from a situation like this. I take a loop and I move it over a bar magnet at some speed v, and that will create a motional EMF, and that'll drive a current around that loop. But relativity says that this picture is exactly the same as this picture, which is a stationary loop that I take a bar magnet and sweep it underneath at the opposite velocity. That's just the same thing, looking at it from a different perspective. And according to relativity, we should get the same results. But how? That loop is stationary, and so there's no magnetic force. Even though there's a magnetic field, the charges are at rest, so they don't get pushed on. How then can there be an EMF in the loop? And the answer is Faraday EMFs. So Faraday EMFs are a new phenomenon. They are not the same thing as magnetic forces. They're something new. And what happens is that whenever you change a magnetic field, so if a magnetic field gets stronger or weaker, or if the magnetic field moves, like if you take a magnet and you move it from one place to another, then the field in some places gets weaker and the field in some places gets stronger. That's still a changing magnetic field. A changing magnetic field creates an electric field, which is a new kind of electric field that doesn't require any charges to make. So it's the same thing that we learned about, positive charges produce electric field lines, but this is a new way of making them. Instead of having charges around, you have a changing magnetic field around. And that electric field is capable of pushing on even stationary charges. Since it's electric, it satisfies F equals QE. There's no V anywhere. And so even stationary charges get pushed around by electric fields. So a Faraday EMF is responsible for creating the induced current in the right-hand side of that diagram on the previous slide. Note that which EMF is responsible. Is it electric or magnetic? Is it motional or Faraday? It depends on your frame of reference. It depends on which thing is moving, and not everybody is going to agree on what causes it. The important thing is that they agree on what happens, and what happens is there's a current induced around the loop. Calculating the Faraday field, the Faraday electric field, is kind of challenging. Fortunately, there's an easy solution. Instead of computing the electric field, let's just compute the EMF using the flux rule. So because of relativity, because we get the same outcome in either case, we have to be able to use the same equation to describe it, even though the reason, the type of force acting on the charges, is very different. Okay. So all the equations for the flux rule involve the absolute value. And I always put that there to remind you that the flux rule tells you how big the EMF is, but it doesn't tell you which way it goes. To find out which way it goes, you have to use Lenz's law. And Lenz's law is sometimes paraphrased as nature abhors a change in flux. What does that mean? It means to figure out which way the EMF goes, you have to imagine the EMF inducing a current I, the current I producing a magnetic field B, and the magnetic field B is such that it opposes the change in flux that originally created it. It's a pretty complicated argument. You have to go through several steps to figure this out. And in particular, the current and the magnetic field, the induced current and the induced magnetic field, may not actually exist. They're hypothetical. What would this EMF do if it were allowed to create a current and a magnetic field? The EMF is real, and so the size of the EMF that you're calculating with the flux rule is a real EMF. It really exists. The current may or may not exist. The size of it depends on details of the problem. Okay, here's an example. Take a loop of wire that's stationary, take a bar magnet, and pull that bar magnet away from the loop. So the field going through the loop is going to get weaker and weaker. That means the flux is decreasing. So there was more field going through that ring. This field was stronger, so the flux was bigger. As I pull that magnet away, the flux is decreasing. So what's going to happen? The induced EMF and the induced current in the ring are going to try to increase the flux. They want to oppose the change. So the flux is going down, they want it to go up. That means I have to make upward pointing magnetic field to compensate for the reduction in upward pointing magnetic field. And that means I need to create a current that goes counterclockwise in this picture to create an upward magnetic field to create a flux, to increase the flux through the ring. If instead I push the magnet towards, I'm increasing the flux, the induced current is going to try to decrease it. It's going to try to create a downward field, and that means I'm going to get a clockwise current. So the direction of the current is going to depend on which way you push the magnet around. Okay, that's it for this video. Hope that clears some things up. Feel free to post questions if you have them. and thanks for watching.